Primordial fluctuations are density variations in the early universe which are considered the seeds of all structure in the universe. Currently, the most widely accepted explanation for their origin is in the context of cosmic inflation. According to the inflationary paradigm, the exponential growth of the scale factor during inflation caused quantum fluctuations of the inflating field to be stretched to macroscopic scales, and, upon leaving the horizon, to freeze in. At the later stages of radiation and matter domination, these fluctuations re-entered the horizon, and thus set the initial conditions for structural formation. The statistical properties of the primordial fluctuations can be inferred from observations of anisotropies in the cosmic microwave background and from measurements of the distribution of matter, e.g., galaxy redshift surveys. Since the fluctuations are believed to arise from inflation, such measurements can also set constraints on parameters within inflationary theory. Formalism. Primordial fluctuations are typically quantified by a power spectrum which gives the power of the variations as a function of spatial scale. Within this formalism, one usually considers the fractional energy density of the fluctuations, given by, whereas the energy density, its average, and the wave number of the fluctuations. The power spectrum can then be defined via the ensemble average of the Fourier components. Many inflationary models predict that the scalar component of the fluctuations obeys a power law in which for scalar fluctuations is referred to as the scalar spectral index, with corresponding to scale invariant fluctuations. Adiabatic, isocurvature fluctuations. Adiabatic fluctuations are density variations in all forms of matter and energy which have equal fractional over/under densities. So for example, an adiabatic photon over density of a factor of 2 would also correspond to an electron over density of 2. For isocurvature fluctuations, the density variations for one component do not necessarily correspond to density variations in other components. While it is usually assumed that the initial fluctuations are adiabatic, the possibility of isocurvature fluctuations can be considered given current cosmological data. While the overall constraints are inconclusive, uncorrelated isocurvature cold dark matter modes are found to be unlikely. Tonto modes. The presence of primordial tensor fluctuations is predicted by many inflationary models. As with scalar fluctuations, tensor fluctuations are expected to follow a power law and are parameterized by the tensor index, and the ratio of the tensor to scalar power.